So today we are going to start, that is your streamline flow and turbulent flow. So let us check what is a streamline flow. Suppose if the water molecules are moving like this, okay, let us say name it 1 2 3 4 like this, okay, and after some interval I check these molecules at this point, they are same, maintaining the same order like this 1 2 3 4, and crossing the particular destination at the same interval of time. Okay, they are crossing a particular destination at same interval of time, okay, by maintaining their same order, same serial order, then that kind of flow is known as the streamline flow. Okay, so let's see in detail what is that. The particles maintain the order and cross any particular point with same speed. Okay, they will cross any particular point with the same speed, right? Then that is known as the streamline flow. Means 1 2 3, suppose they are there, so the 3 point will cross this one with the same speed, 2 will cross this one with same speed, 1 will also cross this one with the same speed. Okay, but what is a turbulent flow? Turbulent flow is that, for an example, if I will take this one, 2 3 4 molecules, okay, after after some distance, what will happen? This one will overtake this two, okay, this two will overtake this three, okay, or one will overtake this four, anything will happen, right? So this overtake will lead to the turbulent flow, that is known as the disturbance creation, and this is happening if there is a higher speed is there. Okay, if there is a much velocity, or you can say if there is more velocity than that of the normal, then you can say the turbulent flow will arrive. So what is a turbulent flow? If when particles do not maintain their serial order and overtake each other, right, then that is known as the turbulent flow. What is the example? Tap water, right? That when you are switching on the tap, the water suddenly it is coming out, so they are not maintaining the serial order, the particles. The water that is coming out from the spring, okay, the spring that is being collected at the river, but the river flow is somewhere, it is a streamline flow, it's a steady flow, okay, that is a streamline flow. But the water that is coming out from the spring, from the top surface, the water is coming and reaching to the down surface with a maximum speed, there also it is not maintaining the streamline, it's a turbulent. At best example is in your home day to day life, that is a tap, water tap. So there you can reach one question, what is a critical velocity? So critical velocity is that velocity of the flowing fluid beyond which its flow will become turbulent. Means it's a threshold point. Okay, if this point, if the velocity of the water is maximum than that this point, okay, then it will become turbulent. That velocity is known as critical velocity. Okay, this threshold point or the threshold velocity point is known as the critical velocity point. Okay, clear everybody? Switch on your mic and say me yes if you understood. Okay, and now next point is that when you can say the water will flow, suppose the water particle is there, okay, and that is having a weight of mg, okay, then this will be your mg cos theta and the opposite will be mg sin theta. So you know it very well, the mg sin theta is responsible for the flow, okay, and that mg sin theta, that theta has to be maximum, right? Then only if there is a surface like this, okay, if this is like this, then the flow is quite minimum. If the surface is like this, then obviously the flow will become maximum. That's a normal condition, you know it very well. Okay, now let's move on to the very important concept, 5-mark long question, that is Bernoulli's theorem. Okay, Bernoulli was the scientist and he gave a very important theorem which has been applicable in each and every sector of the human life, right? And what is that? All the three energies, that is your pressure energy, kinetic energy and potential energy, will remain same okay, throughout the system, will remain same throughout the system. Okay, all three energies, that is the pressure energy, kinetic energy, and the energy due to the potential, will remain same throughout the system. Okay, so this is a pipe that I have taken here. Okay, as you can see, this section is quite broader, this section is quite smaller. This is a kind of section that I have taken, and here the height from the ground is h1, here the height is from the ground is h2. Okay, and area is a1, velocity is v1 here, and pressure is p1 here, and here the velocity is v2, area is a2, pressure is p2. Okay, so it is telling us that p1 plus half rho v1 square plus h1 rho g will be equal to this one. Okay, what is this one? Let us see in detail. Okay, so we know it very well. Work done on a body, okay, work done on a body is force into displacement. So what is a force? Pressure into area, because we know it very well. Pressure is equal to force upon area. So what is force? Pressure into area, right? Pressure into area. So I can write it as pressure P and area into displacement, that is A into L, that is known as the volume. So P into V. Okay, so work done on a body, formula is what? P into V. Okay, that is for a liquid case I'm telling about. Okay, whenever there is a liquid construction that I am saying, I have to consider the area as well as the volume. Okay, now let us see what should be the work done per unit volume. Okay, work done per unit volume, that means what? I have to divide with V. Unit volume means I have to divide with V, and V will be cancelled. So what is the work done on a body? P, right? Why I am considering here unit volume? Because I have to check for small sections. Here what will be the per unit volume, what is the pressure? Here per unit volume, what is the pressure? Here per unit volume, what is the pressure? So per unit volume calculation is there, right? I am not taking the whole calculation, right? And that will be added after calculating the smaller parts that you know as integration. Okay, so what is work done on a body? Force into displacement, that is pressure into area into displacement. So this is pressure into volume, and work done per volume, unit volume is P into V by V, so it is pressure. So how much energy that you are providing? Work done is what? The energy providing. So how much energy you are providing? You are providing the energy in terms of pressure, and in terms of pressure per unit volume, right? Per unit volume calculation that we are taking. So see here, as you can see that I told pressure per unit volume is PV upon V is equal to P. Okay, and pressure upon unit mass, if you want to take up to mass and you want to calculate, that also you will calculate, but it is not in your course. This was not there before, and this is not there now also. Okay, but still I have written this one in order to make this one utilized in your entrance section. So pressure per unit volume, what is that? PV upon V, because work done is what? Work done, you are doing the work in the pipe. You are doing the work in the pipe section. How you are doing the work? By giving a pressure. Okay, giving a pressure means what? Initial pressure you will provide through the help of a liquid. This one will be connected to a tap, right? And you are providing the initial pressure P, okay, per unit volume. Okay, so that's why work done per unit volume is nothing but the pressure energy, right? Anything you are doing the work, you will achieve the energy, or here it is a pressure energy, right? So pressure energy per unit volume is PV upon V, that is P. So pressure upon unit mass is PV upon M, okay, that you can derive later on. And kinetic energy is what? Half mv square, right? So what should be its per unit volume, because we have to take per unit volume calculation. So per unit volume it will become half mv square divided by V, volume V, as I am taking this volume as different symbol, because V and V will be of the same symbol, that's why I have taken like this. And you can write this mass as volume into density. So let us write it as volume into density. Okay, so this is nothing but this section is half into rho into volume into v square divided by the volume. So volume and volume, it will be cancelled. So what is this one? Half rho v square. I am introducing you how much energies are being introduced in the system, in the pipe, that the pipe that you have seen, how much energies are being introduced. One is pressure energy P. When it will get the velocity, it will achieve a kinetic energy half rho v square. When it will reach to a height, this one, okay, here you can see it is reaching to a height, this one, obviously. So during the course, at this point, obviously it is going to achieve a energy, potential energy, okay, and this point also height is there, and somewhere if height is there, obviously potential energy concept is there, right? So if it is also achieving the potential energy, then what should be the potential energy formula? mgh. As you can see here, potential energy is mgh. So what should be per unit volume? Mass, I can write it as volume into density, that is rho into v, and gh as usual, gh whole divided by the unit volume. Okay, and v will be cancelled. The formula is rho gh. Okay, so how much energies are being involved? Pressure energy, that is half rho v square kinetic energy, and potential energy rho gh. Okay, let me go back to the diagram again. You are inserting the water in the form of pressure energy. Because of the pressure energy, you are inserting this one. If pressure is not there, you cannot be able to apply or insert the water inside the pipe. And then during the course, it will achieve kinetic energy. Kinetic energy here is minimum, okay, because it is the starting point, and everybody knows this one, starting point kinetic energy quite less, and during the course the kinetic energy will become maximum, right? So here the half rho v square is minimum and here the half rho v square is maximum, right? And here obviously you know it as the height is maximum, so the potential energy is maximum, that is h2 rho g, okay, is maximum here at this point, and h1 rho g is quite minimum at this point. Okay, and pressure, as you are providing pressure at the starting point, is always maximum, and due to this flowing of liquid, some amount of pressure is being lost, because during a work done, some or during the process is going on, because of that it is being lost. Okay, the energy is, you cannot say the energy is lost, it's being converted into somewhere energy. Okay, it is being converted somewhere into other energies. So the pressure energy at the starting point is being converted to your kinetic energy and potential energy. That we'll see it later on. But remember one thing, who is maximum, P1 or P2? The pressure at P1 is obviously maximum, because you are providing the water from this point onwards, right? So P1 is maximum and P2 is minimum, right? Because during the course it will lose its somewhat of pressure, right? So now let us see in detail what should be the formula and what we need to prove in the Bernoulli's theorem. The Bernoulli's theorem says us all three energies will remain same, that is at the starting point P1 plus half rho V1 square plus H1 rho g will be equal to P2 plus half rho V2 square plus rho g H2. Okay, this one we need to prove. This one is equal to this one. Okay, this one is equal to this one. That only we need to prove. Okay, now let's move on to the proof section. Okay, now for streamline motion, all three energies per unit volume is same. Okay, because we have already found out from the equation of continuity, the volume always remains the same, because how much volume you have inserted, that much volume of liquid will come out, right? Because if it will stuck somewhere, then the pipe will burst, but it is not happening anywhere. Okay, this is simple common sense, because whenever the area is less, the velocity will be more, and whenever the area is more, the velocity is less. So they are satisfying this one in order to maintain the volume as same everywhere throughout the system. That's a different story that we have achieved in the last class. So from the diagram, the energy is given in terms of pressure. Okay, the energy is given in terms of pressure. So what is the given energy? You are giving energy, that is the pressure difference. Okay, what is the pressure difference? At this point the pressure is high. Okay, the highest terminal or the starting terminal, the pressure is high. This is P1, so this is P2. So what is the energy that you are providing? P1 minus of P2. This is the net energy you are providing, right? Because this is higher and this is lower. So what is the energy that is being provided? P1 minus of P2. Okay, so here I have written here energy given P1 minus of P2. P2 is quite less due to distance traveled. I have written, don't worry. And this energy given is converted to kinetic energy and potential energy, because the pressure that is being lost, okay, the pressure that is being decreased, or the energy due to pressure that is being diminished, is being converted to kinetic energy and potential energy later on, right? So now let us write it. What is the kinetic energy that the system has taken, or how much kinetic energy into which it is being converted? So energy given is how much? P1 minus of P2. So energy taken by the system is how much? In the form of kinetic energy, in the form of potential energy. So taken kinetic energy is half. Who is maximum? At this section you can say it easily, your velocity at this point is maximum. Okay, because at the starting point it is quite minimum. Okay, and at the upper section it is quite maximum. So you can write it as half rho v1 square at this point is less than that of half rho v2 square. So what is the kinetic energy formula? Total kinetic energy taken, half rho v2 square, because this is greater, minus of half rho v1 square. Okay, so I can write it as half rho of common v2 square minus v1 square, because v2 is maximum, right? And what is the taken potential energy? As you can see, the height is maximum here. Okay, as you can see here, the height is maximum at this point. So obviously rho g h2 is maximum and rho g h1 is minimum, right? So the formula is rho g h2 minus of rho g h1. This is the formula of potential energy taken through this system, throughout this system, right? And one more thing also you can consider here. Here the velocity is quite small because the area is or you can say area is more, that's why the velocity is less, and here area is less, that's why the velocity is more. That's what also you can consider. But remember, always at the starting point obviously the velocity is small, and during the course it will achieve a highest energy. So the taken potential energy is rho g h2 minus of rho g h1. Now according to the law that we have considered in the work power energy concept, that is energy given is equal to energy taken, that is energy given in the form of pressure difference, that is P1 minus P2, is equal to energy taken, that is half rho V2 square minus V1 square, plus how much energy? Next potential energy, that is rho g h2 minus rho g h1. Okay, now what I will do here, I will just write it in the form of what you can say, just by applying ones one side and twos one side. Okay, I will take one side and two one side. Let us rearrange it. Okay, so this is P1, and when this rho B1 square, this is minus here, right? You can see here this is minus half rho B1 square, it is minus, and when it will go to this side it will become plus. So plus half rho B1 square. And similar thing here also, minus rho g h1, if it will go to this side, opposite side of the equal sign, it will become plus rho g h1. Okay, so it's a very easy proof. Don't forget, only remember one concept, that is what? Energy given equal to energy taken, right? Pressure energy difference and energy taken in the form of kinetic energy and potential energy, right? So now if we will rearrange it, obviously we will achieve P1 plus half rho V1 square plus rho g H1 is equal to P2 plus half rho V2 square plus rho g H2. This only I wanted to prove. Okay, this proves that all three energies are conserved. Conserved meaning is what? Same. In the starting point and at the end point, everywhere the concept is same. Okay, so this was the thing that I wanted to prove, and that one proved by that derivation. That is P1 plus half rho V1 square plus H1 rho g at starting point is equal to this one. P2 plus half rho V2 square plus rho g H2. Okay, so throughout the system, the energy remains the same. All of you understood? Say me yes if you understood. Okay, so now let us see another concept, that is, if I will take, all of you observe it clearly, if I will take this insertion pipe and this one like this, okay, this pipe is like this, okay, and I have just now proved the energy at this point is equal to energy at this point, right? And I need to place this one in the form of work, because if energy is same, obviously the work done is also same, right? So work done is the same principle. If you will do the work, then only you are going to get the energy. That means in this pipe, in this section, okay, in this section I can write it as work done at this point is equal to work done at this point, W1 is equal to W2. Let us me write it at W1 equal to W2. So if I will write like this, what is the W1 formula? The W1 formula, work done formula, is force into displacement. So let me write it as F1 L1 and this is F2 L2, right? So if it is F1 L1 equal to F2 L2, okay, then if I will write this one in the form force, in the form of pressure and area, you know the formula, force equal to pressure into area, right? P into A. So let me convert it, F1 into P into A. So F1 is equal to P1 A1 into L1 equal to P2 L2 P2 A2 into L2, right? P2 A2 into L2. Are you getting my point? Here I am converting my force 1 into P1 A1 and force 2 P2 A2. Okay, now let us divide with the same time interval. Okay, let us divide this one with same time interval t. Okay, so this L1 by t will give me the velocity. Distance over time is velocity v1. This distance over time is the velocity v2. Okay, so now I will get the relation, that is P1 A1 V1 is equal to P2 A2 V2. So this relation I will get. So from here I can write it as P1 by P2 is equal to, if I will take P2 here, that will be divided, this is equal to A2 V2 divided by A1 V1. You just look at this concept and find out what is the only point is going to be concentrated. That is, your pressure is inversely proportional to the velocity, right? This V is the velocity, P1 is inversely proportional to the V1. This was the very important concept that was provided by your Bernoulli's theorem. One part is what? Energy throughout the system will remain the same, and the unique thing that was found from that equation, if work done in all the side is maintaining the same, then pressure is obviously inversely proportional to the velocity. Okay, and this was applicable in various kind of things like aeroplane wings, and you can see the Magnus effect that the bowlers are using to swing the ball in swing and out swing. Okay, and somewhere at some Venturi meter. Okay, all these concepts are there that we are going to study it later on. But remember the concept, what is the pressure and velocity relation? It is a inversely proportional relationship, right? So now let us find it out. how it is working in your aeroplane wings. Okay, so this is the wing that you are being looking throughout this picture. Okay, so this is one side of the wing. You can check this one, you can check the aeroplane also. The aeroplane's upper section are knowingly made of the larger length. Okay, this is being tilted like this. Okay, okay, this is quite bending structure. Okay, this to this, but its lower section is a straight line. Its lower section is a straight line, means the opposite section, it is not visible to you people. This is the upper section, okay, and the lower section is downward, and the downward section is a plane section. Okay, it's a plane one, but the upper section is like this, and knowingly it has made like this. Why? Because we need the upward thrust. Okay, we need the upward thrust. Suppose I will take the particle A, air particle, and B. Okay, this A particle and A particle is flowing in upward direction, B is flowing in the down terminal. Okay, is moving through the downside, okay, of the aeroplane wing. Okay, A particle is going in the upside direction, okay, and B is flowing through the lower terminal of the wing. A is flowing in the upper terminal of the wing and B is flowing on the lower terminal of the wing. As the lower side is of the straight line, so B will take the less time to cover this one. Okay, it will go fast and will cover this whole wing because it's a straight line, right? So what is L upon T? Is quite less, the velocity is less. Okay, that is, what is this one? Length over time. Length over time crossed by the B particle is quite less. Okay, so velocity is less. Velocity is less. Okay, this is equal to V, this is equal to less. Where? In the lower terminal. Okay, that is at the lower section. Now see at the upper section, that is the curved section. I made this length somewhat higher than that of the lower section length, because lower section length is a straight line, this is a curved one. That means I have made this length quite bigger. So here the length upon time is velocity, that is quite maximum. Okay, if it is maximum, okay, if the velocity is maximum and I know the relation, who is minimum? Pressure is minimum. What I need for the aeroplane? I need the aeroplane, this side pressure should have to be less, and the pressure that is being coming from down surface to the top of the wing. Okay, if the wing is like this, from the down to top, when it is taking off from the ground, okay, if this is the plane swing, let me draw again. If this is the plane swing, right, I need from the down section pressure to be high but upper section pressure to be low. Okay, and you can see here at the upper terminal, as it is crossed one, so here the velocity is quite higher, so that's why the pressure is less. And here, as it is a straight line in the lower terminal, so that's why here the pressure velocity is less and the pressure is more. And I require that one only, because if it will provide a lower pressure to the lower side of the wing, then only it will help the aeroplane to take off from the ground, right? So I need the lower side pressure, that means the pressure from lower side to the lower section of the wing. Okay, I need the pressure which should be provided from the ground to the lower section of the wing, then only it will get the height and it will take off. Okay, and I don't want the pressure to come from the upper side. Okay, I don't want the pressure to be applied from the upper side to this section, okay, to this upper section, because if it will be like this, then the aeroplane will sever, or you can say it will tumble there in the what you can say sky, or you can say while taking off there will be a accident take place. So right, so this is the thing that is being happening here. This is the simple example, it is also coming for 2 mark. Okay, what is happening, or what is the application of Bernoulli's theorem? You can write it, this one in the aeroplane wing, and this I have also introduced you from here, aircraft wing, and I have said the same thing as the A and B particle. A particle is covering the larger length, so that's why In the top section, the what you can say, velocity is small, velocity is more, that's why the pressure is less. But in the lower section, as the velocity is less, that's why the pressure is more. That's why it helps the aeroplane to take off from the ground.